Okay. Well, welcome everyone, and thanks for joining us today. Today, Dr. Horacio Tapia-McClung presents us his talk, Interacting and Collaborating with Today's Industry on the Physicist Experience. He received his PhD from UNAM. Nowadays, he's a researcher in the Instituto de Investigaciones en Inteligencia Artificial from Universidad Veracruzana. His line of researchers are data analytics and modeling, complex systems, and statistical mechanics of learning. At the end of the talk, Dr. Horacio will answer the question from YouTube. And one more, we thank everyone for attending this talk. And Dr. Horacio, the stage is yours.
Thank you very much. Thank you for the kind presentation, and thank you very much for the invitation to give a talk with you. I'm very pleased for you listening to me, and thanks for being here also. So I changed a little bit the title of my talk. It's the same idea. Now I renamed it Physics and AI because I am at an AI institute. But I still call it opportunities for collaboration with industry. And it's going to be a very non-technical talk. I would like it to be more like a dialogue between you and us and me, especially because what I'm going to tell you is my personal experience getting close to working with industry. So during the talk, I'm going to show you a little bit of my roadmap to get where am I right now in terms of the work we've been doing together with some companies in Mexico and how we got there and why we got there. I want to talk about what the problems that we've had, the bottlenecks that we found in the way, and where are we, and what we still have to do, and all the opportunities that have arisen, and what we have learned. And also show you a little bit of the actual work that we've been doing. So let me start by giving you a very broad outline of my talk. I'm going to give some introductions. I'm going to try to present what they call Industry 4.0. Then I'll talk about the outreach efforts that we've been doing to get close to the industry in our country. I'll digress a little bit on the general workflow that we all know and use on solving problems, but in machine learning and artificial intelligence, they like to set it up in a very particular way, which is useful to communicate with industry. I'll show you some examples of the cases that we have studied, and then I'll give some closing remarks. Please feel free to interrupt during the talk if you want to ask something. I'll try to be as attentive as possible to see who's asking. The organizers will let me know. Don't hesitate on interrupting me, please. I'll be very glad to try to answer your questions. So let's go to the introductions. A little bit about me. This is the picture that you guys used to do the drawing. Thanks for that. Currently, I am a researcher at the Instituto de Investigaciones en Inteligencia Artificial in Universidad Veracruzana. Here's a very pictorial resume of my past work. I started doing some research on frictional granular material, mostly doing numerical simulations with methods that are similar or derived from molecular dynamics. This was a while ago. And then I moved on. When I came to Jalapa, I started collaborating with biologists who are interested in the behavioral relations, or how spiders behave, or what's the type of behavior they have. Spiders are really interesting animals. They seem boring. They're not. They're actually very, very interesting, despite they seem to be doing nothing. We started working with color identification in a very particular species that is very common here in our area. We did some UV, well, down here we just characterized the different variations of colors that this species can have. Then we did some studies of UV reflectance on the surface of the coloring part of the spider. These spiders are tiny. They're like 1 to 2 centimeter big. So this is a very interesting and challenging stuff to get the data from. And then we've also studied some trajectories of how spiders capture their prey under certain circumstances. So this has been interesting because the biologists who do this kind of analysis or these experiments or observations are in need of a lot of the tools that we learn to use and develop, like basic data analysis from start, but also a little bit more advanced analysis that can help them understand why is the species or the animal doing certain behavior. So I've been actively working on this group for a while. We're also working with another group of biologists that are interested in exploring genotypic networks, which are networks that are connected by mutations of the phenotypes that make each genotype. So this example here, you can see the network in the middle. We have 5 different phenotypes. A phenotype is a way, it's to the, in the gene level, the phenotype is something that characterizes one of your physical attributes. For example, the color of your eyes, or the color of your skin, or the shape of your nose. So those particular characteristics are determined by a certain phenotype. These are networks that are obtained from chemical reactions in very little live things. They're not near close to any big organism that we can know. They are actually laboratory things, but they are real genotype networks. So this colleague of mine is interested in trying to understand how the mutations occur. So these networks are connected between different genotypes, different phenotypes. If there is a mutation that can take you from one node to the other, and sometimes that mutation will change the phenotype. So what he's interested in exploring is how these mutations can happen in these networks. So that's another project. That's parallel to the projects I have on the center, which is previously was called the Centro de Investigación en Inteligencia Artificial. This is the main building that we have in the city of Jalapa. It was recently rebranded as the Instituto de Investigaciones en Inteligencia Artificial just a couple of months ago. So we are a pretty new institute in terms of the name. This center is mostly focused on the classical advanced IA research, like there's a big robotics department. There is the people who do computer vision and image analysis using neural networks and all these advanced technologies. There's a group that specializes in optimization, and there's a group that also specializes in time series, with a lot of focus on financial time series, which you have or might have already heard. Professor Raúl Hernández is the lead specialist on that part. So that's for the introductions. Let me talk a little bit about the kind of preamble, what has taken us here into where we are in terms of the subject of the presentation, which is what we've done with industry. So today they talk about Industry 4.0. And let's do a quick history revision about how we got there. We all have heard about the industrial revolutions. They make us read about it on every time we go to school, and we know, or the history has, they have separated these big changes in industry until recently into 3 big revolutions that were called the industrial revolutions. The first revolution was around 1760 to 1840, a while ago. That was characterized because of a big change in the way that the production started to be done. Like the steam machine was introduced. That was possible to make mechanical production. And it had big changes also in society. Society started to transform from mainly rural societies that were dependent mostly on agriculture and animals farming to more urban. And the factory starts to become the center of a community, and all these social issues that come around it. It's also part of the revolution. So that's why it's called an industrial revolution. So come around the beginning of the 1900s, there's a big change, mostly because the assembly line is introduced in the production, and so there's a big increase in inventions and production. The gasoline motor is invented, the chemical fertilizers start to be used. So another big change happens, both in terms of the production that's occurring and also on how the societies start to gather and start to grow more and more away from rural societies to an increase in urban society. We all know this industrial revolution. Then there's the third industrial revolution that it's mainly in the one many of us grew up. It's characterized by the semiconductors, mainframes, personal computers. The technologies that were available are transformed rapidly from analog to digital. And I have a very small video here, which I want to show. Because I find this particular example interesting, that the music, which is something that we are all consumers and we like, has been transformed heavily, and it was heavily transformed during this time. And it's a good example of how we got from an analog technology or an analog asset to a digital asset. And here's a little video that shows this transition. Today, most of the music that we consume is in digital form, but not so long ago, it was still part of our lives in stuff that we could use with our hands in terms of cassettes and records and all this stuff. Come 2000s, when the semiconductor industry constructs these little devices that are able to hold many and many songs on a chip and play them, and we have a very, very clear example of the transformations that are occurring in this third industrial revolution. And then come 2020s, we have the fourth industrial revolution. We stay online, we do video calls, we work from home, we have to wear a mask. So I don't know if you guys know the Jetsons, but they already predicted what we're living now a couple of years ago. The Jetsons was a very popular cartoon when I was a kid. And who would know that they, like the Simpsons, were predicting all this stuff. So today, the Industry 4.0, of course, refers to a fundamental change in how we live and work, due mostly to the advances on the technology that we have today. And here's a big roadmap for this that was created by some of these world watchers. One of them is the World Economic Forum. The kind of technology that we have today has allowed a change that they are calling the fourth industrial revolution. But what is exactly this fourth industrial revolution, and what makes it possible? Well, you might have heard that in 1 minute, as we speak right now, gazillions of amounts of data are created. And here's a outdated wheel that kind of gives an idea of how many data is created on a minute in the different websites and digital consumer products that we have. And this is just online. We're not showing here the other type of consumptions that we're doing with our telephones and all the other devices that we carry around. But up to 2020, it was estimated that every second, by every person, we were creating 1.7 megabytes of data. it's an estimation that in 2 years alone, 90% of the data that we currently have has been created. So, of course, this is outdated, right? If you read down in the lines, it says by the end of 2020, 44 zettabytes will make up the entire digital universe. We are already on the 2021. We don't know what the effects of the pandemic are on that, but it's probably increased. So we are really, really in an era in which we are producing a lot of data, and we are also consuming a lot of data. And so the technologies that have developed around this big data, or these big amounts of data that are created, has also worked as a driving force and a trend into the developing other related technology that has to be used to be able to process all this data. So we need new software, which has been developed. We need new hardware, which has been developed. We have connected devices, and they keep developing. We have cloud computing. This creates more big data. We have better collection and transmission of information. It can be done in real time. We have mobile computing. And all these areas are developing really, really, really fast. So today we are already talking about smart cities. There are cities, some cities that are completely covered by sensors, and they can actually respond to many of the things that happen in the city. There's a big example in Spain. The IoT, the Internet of Things, the development of robots. I don't know if you've seen the last robots of Boston Dynamics, but it's a huge step from the first examples they were showing. What's referred to as the cyber-physical systems, smart machines, smart products, smart services, etc. So these areas are also developing very rapidly, and of course they generate a lot of data. So this is a big wheel of what they call the fourth industrial revolution. It's a change in which we are merging the physical, the digital, and the biological worlds, and fusing all the technologies in ways that create, according to the this, I forgot the name of the World Forum, they also create promise and peril. So if you are interested, you can go and check this site here. They have really, really very nice animations explaining what these trendings are today, what's the fourth industrial revolution, what's related to it as technologies that are being developed, that are being innovated, what new skills are demanded on the market, what's required in terms of governance of data, what are the ethics behind it. So it's a very interesting road and a network of the issues that are surrounding this new idea. And of course, it means digital transformation of businesses. And this digital transformation of businesses, that it's already occurring and some companies are already transforming, is one of the motors that drive us to try to explore how we can collaborate with industries today. And of course, what is one of the drivers of this is science. So a lot of this is possible because of many of these, if not all, new technologies and advances are possible because of science. So it's a medular part to keep doing science, but also to use this scientific knowledge to participate in this revolution somehow. So okay, that's the idea of the Industrial Revolution. Number 4, it's much broader than what I have shown here. There's a lot of work either actively trying to make it happen, transforming into digital industries and becoming a 4.0 industry ready, which very few companies in the world are actually completely 4.0, but there is a tendency into that. And a couple of years ago, I was working at this center that's called Laboratorio Nacional de Informática Avanzada, which is a private research center here in the Ciudad de Jalapa with that has been around for about 30 years, developing and working in both research and applied technologies with a focus to how to use these developments for companies or for industry to help them with their processes and make them more efficient. So they have a lot of experience, a lot of knowledge, and a big network contact with companies and industries around Mexico. And by the time that I got here, I think it was around 2014, there was a big effort on trying to identify certain ways to collaborate between academia and industry. And they had been working on a very particular model that it's called the Industry University Cooperative Research Center, which is a program funded by the National Science Foundation, the equivalent to CONACYT in the United States, which has as a mission to create long-term partnerships between industry, academia, and government. And so it's a very, very curious and very interesting project that they run in the United States, because what they do is they bring together industry that has certain particular problems or interests, both to solve the problems or not to solve them, or to research, do some more basic research into those problems, and they pair them together with the universities. And it's not that they pair them, I mean, they invite universities and industry to pair and join forces to develop these research centers that work together to develop these solutions mostly that the industry needs. So the NSF gives a lot of money for the first 5 years, and it's evaluating very, very closely the relationship between industry and companies, and I mean industry and academias, how they work, how they develop. After the second period of 5 years, which means 10 years if the center survived, then they stop funding. They reduce the funding, and they only keep funding for a certain administrative work for the center, because they do it in such a way that by 10 years, they find that this center is already mature and it's already working by itself, both as a center that's solving problems for the industry, but also that is getting money from the industry to work. So this center in particular, which I'm showing here, the IMS, the Intelligent Maintenance Systems, at that time had been 15 years in the program, and it was already a completely mature center. It was already funded by itself, by the partnerships they had with the companies that they had been working. So it was one of the biggest examples of how this program is working in the United States, and it's one of the golden examples that they always said, well, it works, you just look at the intelligent maintenance systems. So this Lania Center, where I was working at, had already established a very close relation with the director of the IMS. And I was put on board of that project, and I got to know how this program, the NSF program, worked, and how the IMS was, sorry for that, how it was constituted as a center. So this is basically a diagram of how they are, what's their organization. So there's these academic institutions, which together with the companies are the core of the center. The academic institutions are mostly universities in the United States, and of course departments, research departments in the United States. In this particular case of the IMS, the main center is located in the University of Cincinnati in Ohio. The other academic center is the University of Texas at Austin, and the third one is I think the University of Ohio. It's the third one, also in Ohio, but it's not the University of Cincinnati. So the organization is that there are these co-directors from the academic institutions. There's an industry, an IAB, which is a board of advisors, which basically is the representation of the companies that are participating in the center, and they closely look at the relation of what the center is doing for the companies that are partners. So below that, there's the activities that they do. Of course, there's the NSF. The NSF only acts as an observer and an evaluator for the relation between the members of the center. And of course, when a center is mature enough, they can have satellite centers. This center has a satellite, you can see in the map on the right. There's a satellite center in Canada. There's another in Brazil. There's another in Italy. I think they have a couple in China. And we were very close to open or create a satellite center in Mexico, in Lania, thanks to the efforts that we were doing at that time. So I'm going to go a little bit on that. This center had a very particular toolbox that they developed in order to reach companies and actually be able to offer services that the companies need. And this table here shows the 4 main areas of applications that the center was working on and the type of analysis that they were doing on the different areas of applications. So they were doing signal processing, they were doing feature extraction, they were doing assessment of the health and diagnosis of the health of the assets or the machine. They were predicting the performance, how well it was working. And this table shows the type of techniques and algorithms that they were using. And of course, when reading this, it's really nothing that we could not understand with the professional education that we've had. And it started to become interesting that they were actually putting together all this toolbox and algorithms to be able to provide a very particular and interesting service to companies in a very ordered way, which allowed them to actually get results for the company. And so we learned a lot about how they did it. They have a lot of work done in this. If anybody's interested, I can point you to places where you can read more. But what's interesting here is that all of these techniques that they put together into this toolbox, they tested them and they tried them and they compared them and they used them doing actual work and publishing actual work done for the industries. So it's a very, very interesting way of working of the IMS, because they say they have a new partner that has a certain problem. They somehow get data from them, and they use this toolbox to work out the problem. And because of the partnerships they create with the companies, they are able to publish the results and present, for example, for this particular kind of problem, neural networks is better than a Gaussian mixture model, or they are able to compare different parts of the problem thanks to this data that it's doing. So they have done a very long-term, very important work in this term, supporting all of this with actual scientific work. So the director of this center likes to say that they do this type of consulting to industries, but they do it in a scientific way. And once you meet this person, it's indeed how he has. So we were we had the opportunity to learn a lot from this person who's been working for a long time on this relation. As I said, we were close to become a regional site from Mexico. What happened and why didn't we become one is that at that point we needed more support than just what a little research center can do in little research center in Jalapa can do. So we started doing a lot of outreach and work with CONACYT. CONACYT at that moment was also kind of interested in trying to create these spaces where there could generate more relations between academia and industry. And we had been lobbying a lot with them that this model of the NSF was a good model that we could translate to the Mexican scenario, or at least we could try to do it. On the same line, NSF and CONACYT, on a very different level of collaboration, we're also doing things together. And one of the projects that they were working on as institutions or government institutions was finding ways to kind of replicate or to produce this similar model of the industry university partnerships in Mexico. So it was lucky that they agreed on that, and that we had been working with this, and we had a good contact with these people in the United States. We got the chance to meet the people from NSF, and they were telling us very, very closely how it worked. So we had a very clear idea, and at that moment, fortunately, CONACYT opened a call for proposals. I think this was around 2016. So there seemed to be some interest also from CONACYT to push this, and we were lucky to be in the right moment and with the right people and doing this thing to participate in that convocatoria. The convocatoria was called Consorcios Binacionales con la Industria, and it was a very CONACYT thing, a very but we got the proposal. We got the money. It was not very much money, but the idea was that with that money, we were supposed to partner with a center from the United States, from the same program as I have just presented, the NSF's program, and that we were going to create a binational center together with that center in Mexico. So because we already had the relation from a couple of years ago, it was very natural that we got this support from the CONACYT, and we were able to run our project trying to develop further this regional center, to establish it. And from there, the next step in doing this outreach or trying to fulfill the whatever we said we were going to do in the CONACYT proposal, we had to actually start looking at companies. So we had already done it. We were traveling a lot around the country and visiting places to get to know the companies and see what they did and what were the lines of work or interest they had. What was the current stand on collaboration with academia? And we found a lot of walls on that. It's very, in a country like Mexico, unfortunately, the relation between academia and industry is very, very far apart. And I kept asking people from industry, from the companies, what were their experiences with academia? And of course, everybody had some experience with researchers or with CONACYT or professors at universities and projects like that. And the majority of people I asked this told me, the thing is that people in academia don't really understand what we need in the industry. And what has happened is that they come with these projects and they say, oh, we have this tool, we want to solve this for you, so tell us where we can use it. And it doesn't work like that. It can't be done like that because we don't need it like that. So I started learning a lot of how the industry worked and what the differences are from in Mexico, and trying to be more sensible into, well, how can we get to industry so that they give us their problems so that we can work on them. And it's clearly not going to be like this. It's not going to be like I'm just calling, hey, hi, I am Professor Horacio from this university, and I want to work with you. It has to be a very, very long-term work, and it has to be done differently. So with the CONACYT proposal, what we did, because one of the goals, one of the objectives was to actually establish some collaboration with the industry, we decided to do, okay, this is just the relation we had. So we decided to do what I called at that time the data challenge industrial. You probably have heard of it in another talk that I had given somewhere else, because I kept doing like my commercials for this. So what happens, what was the data challenge, or what is the data challenge industrial? So after all this research with companies and trying to get together to them, I had to come with some ideas to actually bring companies together, bring companies to us and start being able to work with them. And so I thought that maybe using students could be a good way to attract companies and to attract them into actually looking at what we could do with the problematics and how we could approach their problems and probably propose solutions that could be used. And so the Data Challenge Industrial was born as a competition. The Data Challenge, that's why it's a challenge, it's a competition in which companies give us their problems and give us their data with a very particular specific question that we developed together with the company, with the organizers. So one day when the challenge occurs, a lot of students come in teams and they sit down with their computers and work towards a solution of the problems. And so it was an experiment. First I wanted to do a kind of a hackathon thing, because it was in the air. Oh, everybody's doing a hackathon. Let's do a hackathon. But then again, I was advised not to use the idea of a hackathon because the students weren't happy with that. And of course, this is a free event. We organized it by ourselves. We had the only support we had at this time was the CONACYT grant, that we could use some of the funds to do this. And the idea was to attract the companies. So we partnered with a company that got really interested in the idea of this model. And they said, okay, we are on board. We are a company that do this particular kind of thing, and we will give you data and we will work with you towards a problem. And so another part of the story is how we organize this, because it's a real complicated thing to get together about 200 students to work on a problem like this, but it's a really fun experience. And the main idea of the competition is that we could offer a space for students and practitioners that were interested in data science, or that they had some knowledge on math, statistics, physics, engineering, computer, but it was completely based on real industrial data. And so this is a goal towards a certain population, say the students. So why? Because we also want to capture good students, because we want to be able to have the best students in our graduate programs. So this is one way also to show them what we do, what we have, and what we can offer, and maybe attract them to participate in our programs. But the other one, which is also as important, was that it allowed us to reach potential industrial partners and hopefully generate long-term collaborations with them. And as it went by in the future, we have been able to strengthen this relationship with the ones that we already partner with. We've had the opportunity to have people from who actually work on the front of what we call today the data science. So here, Alfredo at that time was an engineering doing data science at Uber Technology, the company that sends us cars whenever we want. He gave a talk there, and here are some examples of the challenges that we had. On the first the first one we had what we call the DCI 1.0. We had to analyze some data from telemetry So this is the company that was interested in this, and they specialize in doing in capturing data of moving cars or moving trucks mostly. So whenever you see a car or a truck that's moving assets on a federal road in Mexico, and it says this car is protected by satellite, this is the kind of things they do. And they had been growing for years, collecting a lot of information, and they were in a point in which they had to restructure themselves as a company to be able to continue growing at the scale that they were doing. And at that point, they were also considering in implementing and using these new, so to speak, ideas of machine learning and data analysis up to a higher level from what they were currently doing. So we were able to partner. We did this data challenge with them, and it came up really well because it was a very interesting problem that they posed, and it was a very interesting challenge in terms of the data that they gave us, and it created a very long-term partnership with them that we've been reaping a lot of good fruits from that. The next year, we worked with the local industry of coffee. As you might know, the Jalapa region where we are located is also famous because of the coffee production that we have here in the region. And there's a big industry in coffee, but it's interesting that it's not a very technology-driven industry. It's still a very analog industry, if we can use that. And it turns out that there's a group that's doing a lot of research in terms of the production and the biology of the coffee that has been gathering data for a very long period of time now, and data of a very particular coffee that is produced. This is coffee that gets exported and sold in different countries, and it's a very high quality coffee though. So it's a very particular market that consumes it, but most importantly, a very particular region from the states in which they can find this coffee. So it turned out to be a very interesting challenge in terms both of the problem and the data. And next years we had, I'm sorry, also a company, a local company that has grown since then a lot, not because of us, but because they have a very particular model of business, but they have grown. And this company basically is in the sector of telephone repairment. So every time you break your telephone screen, you go with them. So they had a huge database of all their clients, and part of the challenge here was to clean their database, order it, and get some information from it that could be useful for their business, right? For their market, and see how they could or not, from the data we had, offer different services to their different clients. So we went up to the number 4 challenge. So every year we were doing one. We also had, here's a picture with the supporters, but they're not our, they only support us in South. There's only 1 or 2 that are actual partners on this. But as you can see, there's a Python Software Foundation, because at some point, realized that we could be also using this event to offer something else to the students that were participating. So we've been gradually growing it and incorporating some programming workshops in which the students can also take a little bit more of knowledge. And in one of the editions, we had another scholarship or another grant from the Python Software Foundation to actually do the workshop. And the other ones are some of the industries that have participated with us. As you can see, if you don't know, you might not know, you don't have to know because you're on the other side of the country, but Tenaris Tamsa, the second logo that you can see there, is probably the biggest company that produces steel tubes for the oil companies in Mexico. So I think the Maristamsa is at the same level probably as Grupo Modelo or Cemex. I mean, it's a huge company. It's a multinational company. Its main center is based in Mexico. It's based in Veracruz, and it's a very difficult company to reach because it's a very, very big company. But they got interested in our competition, in our model, so they participated very actively, and well, that gave us a lot more experience and opportunities to reach out to companies. So slowly and steady, for about 5 years, we've been generating this event, or this, now it's a little bit more than an event, but this activity in which we are able to get to students, I mean, get to companies and actually convince them that it's worth showing us their problems, giving us their data, and letting our students try to solve their data. And it's a great opportunity for both, because at some point they can actually hire some of the students that are there, or invite them to participate on their processes and become part of the workforce. And for us, it becomes a very, very interesting bridge between the three main entities that work on this, which are the companies, the students, and us, the researchers. And one of the things I want to call attention, which I always found and still find very interesting, is that in the 4 competitions that we've had in the last years, always the physicists have been on the first place, always. And it has nothing to do because of the fact that I'm a physicist. It has nothing to do because of the fact that the challenges are oriented towards physics. They actually have nothing to do with physics at all. It's just that, to my view, the physicists have a very particular training that allows them to solve or propose solutions to these kind of problems. So it's an interesting thing that always the physicists have won. And here's the first team that won, and they were very happy because the company gave them as a prize. We didn't consider prizes. We don't give prizes because we don't have resources to give prizes. All these activities are free. But the companies get so happy with the event and how it happens that they actually ask us, okay, so what do we give them as a prize? So they got like new models of iPads given by the company, and they were doubly happy. And then they were in the news, in the university news, and everybody was looking for them. So it's been a really interesting path, the data challenge. And from there, we started generating actual collaborations with companies. And this is the company that supported us from the first, or that we partnered with in the first challenge. And from there, we started actually working into what their the problems were. But at this point, and after having all these talks and visits with other companies, what I realized is that I can't go with a company and ask them, okay, so what do I do? What do I help? Or here I am, and I'm going to do this. Instead, I had to get to know very closely what their processes are, what their problems are, how they work with them, how they actually try to solve their problems, and be more first like an observer, trying to understand what's the process and how it's happening, talking to all the engineers, talking to the people who does the software and does the data sets and gathers information, and going into the actual field. They mostly trucks like the one in the image there. And I realized that we can't do that as a research. So who does this? Students do this. So we partnered with this company to have one of our brightest students, which is not a physicist, but it's a mathematician, and actually work with them together. And he got a scholarship from the company to go and do a research visit in the University of Cincinnati with the IMS. So he was there for about almost 4 or 5 months, learning the details and the techniques from the center that had developed one of the most used, or that had this toolbox of algorithms and techniques to work with industry. So he was there, he was an insider, and he was learning how they actually do it. And he came back here to Mexico, and he gave us more knowledge into how the center do it. And we started trying to merge that into the reality of Mexico. And it worked very well with this company. So now he's, okay, don't mind too much about this, but basically the problem that they were looking here is, how do I know only from telemetry data when a truck should receive maintenance? So this company monitors all the sensors that these trucks have in the motors, which are very complex machines and very, very complex systems, but they are monitored, and this company gets all these numbers at regular intervals of times, and they want to predict, or they want to know. One of the questions they wanted to know is, when should a truck receive maintenance? And why is this a question? Because you would say, okay, well, they must have maintenance plans. You know, this is just like your car. You go to the car shop and you say, hey, I need an oil change, and they give you the oil change. So these cars probably have one, the scheduled maintenance every more or so number of kilometers. And indeed they do, but sometimes they don't get the maintenance done on schedule because they are using these units. They have to be moving, or sometimes they don't do the maintenance as they should do it. So there's a lot of issues there, I mean, a lot of problems and different types of problems. So one of the things they wanted to know is if one of these assets is moving down the road and it's going to the other side of the country, can I know from the data if the truck should receive maintenance, and how long before this is a critical maintenance that it should get? And this is of course important, because if one of these trucks breaks in the middle of the road, it's the costs are huge, right? One of these, both of fixing it and moving it and delivering the cargo. And in general, for a company, if one of their machines breaks and has to go through non-scheduled maintenance, then it increases the costs in a very, very considerable way. So companies want to avoid these extra costs as possible. Okay, so this takes me now to what I call the general workflow that we've learned is done, is applied. I call it here general AI workflow, but it's just to give it a sense of this order that it's useful to be able to communicate with companies. And that's a particular experience we have learned. Companies like this kind of structure where they can actually, in some sense, see or understand each one of these parts. And as you'll see, this general workflow is nothing different from what we do in any of the sciences that we professionally do every day. It's exactly the same methodology. We have a problem, we have to get data for the problem. How do we do it? Well, if we can do an experiment, we do an experiment. If not, we do a simulation. So it's pretty much the same workflow that we had. It's just that if it's structured in this kind of flow way, which I'll describe very briefly here, then companies tend to understand it a little bit better and are able to know where they can actually need these kind of things, and if they're ready or not to do those steps. And it's going a little bit in the direction of what the IMS kind of uses. So you have an asset. Doesn't matter on which sector you have it. No, it can be an elevator, it can be a helicopter, it can be a power line, it can be a motor, it can be a PCL, it can be a cutting machine, it could be a photocopier. And you have to gather data from it. And you can either gather data to just monitor the health state of the asset, or because you have a particular problem you want to take. But one of the things that industries have been doing is just take the data because it's good and it's important to have a baseline of historic data of your process and your assets. And then you apply a lot of data cleaning, data transformations, depends on the particular problem at hand. In this example, they are using some principal components, and then they're getting the distributions along the principal components, and then deciding according to the intersections of these histograms along as time goes, if the machine is failing or if it will fail. And finally, they can assess a prediction or propose a prediction of this based on the historic data that they had gathered. And the last chart is just one cartoonish way of showing an output that is useful for the user or for the worker or for the company CEO or CTO or whoever takes the decisions. I mean, in reality, another thing that we have learned is that people who are at the very high levels of a company are not interested in all these points and these histograms and all of these lines showing here. They don't care, they don't understand, and they just want to see a panel that says work, not work. All of the things that are inside, you have to go to the right person to be able to do it. And this also brings another thing, which is when you're working in these kind of things, you have to talk to a lot of people and you have to understand the problem very clearly to be able to perform these kinds of things. So in general, the workflow goes like this. We have a problem, we gather data, and we have a very, very non-finishing loop where we prepare, explore, analyze, model, prepare, explore, analyze, model, and when explore again and prepare, and maybe our data is not good and we have to do it. And it's exactly the same workflow that we have. This is very schematic here, but most of the times we have data that's being gathered from a complex machine or for a complex atom. It could be temperature, pressure, torque, and we have sensor data, right? We have to prepare it in some way. What happens if we are able to gather data on different states of the system, of the complex machine, then it's much better because we can have comparisons between different modes of operation. And many times it's not possible to do that, but one of the lines of research and development that it's been catching up, and I mentioned briefly before, is what it's called the digital twin or the cyber physical system. Because nowadays with the technology we have, we can actually make digital copies of the physical asset that we have and feed those numerical models with actual data from the physical machine and run different conditions on the numerical model and create synthetic data and see what could happen in different operations or conditions of operations. So now it's a reality. I mean, it's not a completely it's not a consumer thing. Not all the companies are able to do it. Big companies are doing it, and of course, it's not a exact physical representation of the data. It's made by parts. It's made. I mean, the relevant parts are simulated, and the relevant parts are monitored, and they are. There's a whole computer and software language for these kind of things. But you can create synthetic data of different conditions, and you can use that to actually study how is the asset working. And then once you have the data, you have to prepare it, because as everybody knows, when we have data from any sensor, it never comes as we want it. You have to clean it, you have to pre-process it, you have to be sure that there's no missing values or anomalies in the reading, which are due to noise and stuff like this. So there's a whole set of techniques for doing this, but mostly it depends on you as an analyst in understanding the problem, in understanding where the data comes from and what it means and to what it is related. We have found cases in which if we make any assumption about the data, then we can be wrong. So we have to go back to the company or to the owners of the data or those who generated the data, and we have to tell them, hey, what is the meaning of this? Why is this happening? Why is this like this? And because they know how the data is created, they can clarify laws and they can help to do the right pre-processing here. Then it's typical to do what it's called the feature engineering, which mostly is to find some indicators from the data that help to separate the conditions that you have. In particular, questions that could be interesting is distinguish normal from non-normal operations, or predicting what they call the remaining useful lifetime, which is how long can it work like this before it fails. And there are a lot of techniques in many processes. These are just transformations from the space to the frequency, from the temporal space to the frequency space, and we get the fundamentals, the frequencies that are most relevant there, the width of the frequency. If you're working on the temporal domain, then you might want to look at anomalies on the reading that are unexpected, that you don't, they could be shifted, etc. And now, with that idea, or with that general workflow overview of the workflow of how it's done, I want to just present some simple cases that we have worked on with the data from companies that we have been collaborating with. The first example I'm going to show you doesn't actually come from any company that we have worked. It was one of the first explorations we did into this, and the data comes from something that it's called the Prognosis and Health Maintenance Competition. So every year there is a society for prognosis and health in industrial systems, and every year they make a competition in which they give data from a particular problem to the participants of the competition. This competition takes place on the annual Congress of this society. So before pandemic, they gathered together in their conference, and the students would register for the competition, and they would give them the data. They had to work towards the problem that that they post. Pretty much the same idea that we have with the data challenge, except that we don't do it during a conference. So we took this example in order to kind of learn the kind of language they use, the kind of workflows they had doing, the kind of techniques and algorithms they did, but we wanted to use our own approach that we were working at. And it's basically an analysis of time series. And the problem had to do with, you had a field of anemometers that had readings of mean speed, wind direction, and I think temperature. And you were asked to find if the anemometers were working correctly, or if they were working outside of I think 5% or 2% regime of normality. And the problem here is important because whenever they're going to put a farm of these, I forgot the name for the, whenever they're going to put a big farm to have eolic energy, they first have to assess if the place is actually a good place and they have enough wind. Otherwise, you won't get the energy output from the investment of the farm. So they place anemometers, and they place them in different towers at different heights and positions, and they measure their data, and they know that some of the anemometers are working well within this 2%, And the task was to find if any of the anemometers were not working fine, and how far from this 2% they were not working fine. So, well, this was a training thing. A student did all these observations or these measurements and analysis. The next example has to do with fuel consumption. So this is a project that we've been working with this company that we started from in 2016 with the data challenge. This is a very important problem because, and it's actually relevant not only for them, but to anybody who has a fleet of these trucks. You know how fuel is one of the big, or not one of the biggest, the highest or the more expensive thing in the operations of these trucks. That's the most expensive of the parts of a truck. After fuel consumption, it's the batteries of the trucks, and then the tires. Those are the three most expensive things in this. But the gap between the batteries and the fuel consumption it's crazy. I mean, fuel is expensive, and these beasts use over 1,000 liters of fuel on each trip. So it's a huge problem. It's super expensive, and then you have to add problems like, well, there's the huachicol, which I don't know how to translate in English, but basically the stealing fuel from these trucks, which it turns out to be very, very easy when you think that these things are moving at 2 kilometers per hour, because these machines are carrying cargo. They are taking heavy loads from one part to another. They are crossing the roads of the country, but they are moving really, really, really slow. So it's very, very, very simple to come up with ways to steal fuel from these trucks, and that makes it a big problem. So the fuel consumption, or monitoring of the fuel consumption, it's an important problem. It has not been solved. It's a very challenging problem because it's not easy to really identify all the things that are going on in there, and also there is not good data on it, because I mean, now we are asking, well, we can have good data, yeah, but these cars have been running for maybe 5 years, and they are not adapted to be censoring what we need to be able to determine the fuel consumption from the tanks. So here we have an example of how the sensors that are measuring the level inside the tank are what they are reading. On the left, the colors indicate if the unit is moving, which is in yellow. It's less dark, it's clear, and darker means that the unit is actually moving. The big spike that we see at the end of the first graph means that there was a refill of the tanks, so they get filled up to 100% or almost 100%. And then we have another trip. The flat plateau you see is because the unit is not moving; it's completely stopped. And then it starts to move. It starts to realize a long trip, and you can see a very clear decline in the consumption of fuel. The both lines that you see are each tanks. These units have 2 tanks, one on each side, and these lines are monitoring the level of fluid inside each of these tanks. So what they do with this kind of information is that there's an engineer that's looking at the screen, and whenever they get this data from the units, they label it saying, if you have an increase in the reading, the engineer is trained to be able to say if that decrease is a real decrease, real meaning that it's actually part of the motor using the fuel, or if it's not real, meaning that somebody is taking fluid outside of from the tank, which happens. So they can see it on the screen, but it's a very, very subtle thing. I mean, it's a very specific domain knowledge that we don't have. We speaking as an outsider. It's somebody who's very well trained to do this, and he can say this is an extraction, they call it. This is an extraction. This is normal. This is normal. So they are labeling different points along time with extractions and normal. Except that there are not many cases in which they have extractions, fortunately. I mean, these kind of companies don't want to have illegal extractions from their fuel tanks. So it's really hard to come up with one of these novel methods of artificial intelligence where you say, oh, okay, well, I have labeled data. I'll just run a super duper convolutional neural network and have a system that's able to train, that's trained to be able to say if a decrease in the level is good or bad. We can't do that because we don't have enough data in these cases. So we have to come up with different readings in the sensors and different things. When we were working on this, one of the things we understand was a very basic question, which is how is the level in a cylindrical tank, how does actually change with height? And it turns to be a very, very, very nice mathematical problem that turns out the engineerings of the company got all wrong. So they did a lot of their calculations in a wrong way, and they were underestimating the volume that they had. So we had an interesting contribution to them just by analyzing a very, very elementary question that has a closed solution in math. And from there, some other things that are interesting came. For example, because this is a numerical model, we can change the actual shape of the cylinder tank, and we can put different tanks. And for example, it is known in the tank literature that if you change the edges of the tank, and so that the tank is not a cylinder anymore, and it's rather a cone tank, or it has a cap that has a toroidal structure, which are the 3 tanks that are used in industry, then there is no closed solution to the problem because of the nonlinearities that are introduced when you change the shapes of the extremes. And it turns out that all the engineerings, if you check the literature, everybody uses approximations based on just a rather engineering perturbation of the shape here. But we can actually do the numerical integration with the computer by changing the shape. And our method is, because it's numerical and it's exact up to the numbers that the computer can give, we can get better results in a faster time by doing well, not in a faster time, because that's the other one's a formula, but our results are more precise than the ones that you get with the formula that all engineers use. And that's because we're doing a numerical integration inside of the shape. So it's interesting that we could go through that way. And the other thing that we could do with this model here is that we actually feed it with data from the sensors. So it's a sort of a cyber physical system or digital twin of the tanks. So we are looking to see if this is of interest for the companies to have a little agent in their systems that is actually doing these calculations in real time using their real fuel data, and that they can monitor different conditions. For example, one of the conditions that they could do is they could do simulations of changing the velocity of the truck and seeing if the tank level will change, if it will go up or down, and that will allow us to create probably data that we could use in a machine learning model to be able to predict if an extraction is good or bad when they are monitoring the levels of the fluid. With this company also, they track the cars in a they have the geolocations of all the trucks. In this map, you can see all the roads that are traveled with these trucks. This map is made up with 11 million locations of the trucks There is no other overlay. It nicely creates the map of the country. And you can immediately see the complex structure of the road network that we have in Mexico, and also where there is more density of trucks. Of course, here we're not taking into account the speed of the trucks nor the times. I mean, we just overlaid all because we were doing some explorations into the visualization. We wanted to be able to and interact with 11 million data points. And so it turned out to be a map like this. But what we can do with this is a little bit in the, the famous problem of the Königsberg bridges, in which a city is mapped into a network, and then you can understand what the network, the city according to this new map, which is a network. We did something similar to trajectories from different cities around Mexico. With this same company, because they track all this information, here's an overlay of a very particular process of distribution in a city. This is Minatitlan, Veracruz. Minatitlan is a big industrial city that's nearby Coatzacoalcos. Coatzacoalcos is a port in Veracruz, a very important port. So a student took this data and converted it into a network, which is a very natural transformation to see all of these trucks. It actually, Google does it all the time. Unfortunately, Google doesn't tell us how to do it because they don't want us to do it. So we had to do it by ourselves. It's not very complicated, but the complications come in another ways, which I'll get in briefly. So we had cities, these cities here. We have Minatitlan, Celaya, Mexico City, Guanajuato, San Luis, Querétaro, Morelia, and Tijuana, a different number of trajectories or routes for the distribution at different days. So this is the period of days that were spanned, approximately 3 months of data. And what we have is we have a point for every 4 minutes that contains the location, the speed, and a little bit another information which have to do with some sensors of the motor. And what we wanted to do here is convert them to these networks and try to study this distribution among the cities. So the reason we wanted to do this is because this distribution of consumer goods, so these trucks that are being tracked here, they distribute consumer goods locally in different cities, but they are the same company. So imagine it's Coca-Cola, and Coca-Cola is distributing in Minatitlan, and it also distributes in Celaya, and it also distributes in all the other cities. So it's the same company, it's the same consumer good, it's the same product, basically the same operation, but in different cities. So we wanted to see how this distribution of the same thing behaved in such a way, or how it behaves. Actually, we want to see it. The problem here's an example of the routes overlaid again, but the problem that we had here is this is an example of the real trajectory. The blue line with the red dots corresponds to the data points that we have from our partners. So this is the truck data. Every 4 minutes and you can see immediately that we have some troubles here. For example, on the yellow line on top, we have a red line that it's just not going through the road, which is not possible because these trucks are moving along the main roads. And you can see also on the right side, there's like this little triangle, which clearly missed the road, but it didn't just appear on the other side of the road. So this happens because in the 4 minutes that are in between these data points, the car was in the previous position and then it's in the next position, so we have registered this. But in order to be able to create the graph in a correct way, we needed to fix this. So we had a student who, again, was a physicist, and he worked in the company for about 3 months and creating this reconstruction. He actually wrote a nice package that reconstructs the trajectory at every point. So here again, you can see the red points are the original data, and the green points are the reconstructed trajectories with his solution. So he did this for the company because the company knew that they had that issue. They knew that Google had already fixed it, but Google will sell it to you if you want, and they needed it for their process. So the student had the chance to work on this and do the reconstruction. And then when we have all this network, we can study the properties from a network point of view. So here's San Luis Potosí. There's a representation of the network of the distribution, the trajectories of distribution. Here's a frequency of the nodes, which I think we still need to work on this, but this is what the student reported in his work. Here's Mexico City. We can immediately see that communities are somehow created in this map representation. And again, here's the node distribution. Guanajuato is here, and its distribution also. And Minatitlan, the one that's here in Veracruz. It's also, there's a little community there that seems interesting. And finally, what I wanted to do, just an extra idea, was to see how these routes or these trajectories, these routes of distribution are in somehow related or correlated with where the actual stores are. So the points you see in blue in this map correspond to all the stores that potentially sell this consumer's product. So in Spanish we say las tiendas de abarrote in Minatitlan. So the little stores where they could sell it. And on the right you see the distribution of the minimum distance that's starting on one of these stores. What's the minimum distance you need to travel to reach another of these stores? Unfortunately, we were not able to go further with the comparisons here. So this is ongoing work that we need to refine, and we're working on it. And finally, another example, because of the kind of data that we're trying to analyze. This is an example of anomaly detection in the motors of a big tube manufacturing company. And what we're basically looking at here is the current of the motors of one of the bands that moves the material, which is relevant for the production because it transports material inside the factory from one side to another after it gets converted into one of the principal parts. So if these motors fail, the band stops moving and the material doesn't get moved to where it has to go. So the production stops on one side and then it has to stop the other because it can be a continuous production. And what they have here, the first two rows that you see are normal operation. And then around the middle of the third row of the data set, there's an anomaly. There's a change into from what's reported as a normal behavior into a non-normal and anomaly behavior, which can make the motor fail and the production stop. And here, I don't know why, no, sorry, but this time series I'm showing here is just an amplification of the one that you see behind the back, which I can't fix here without messing everything. But of course, this is a big data set, a big time series with all of this behavior that we're looking in red being clamped into a whole 24 hours of data. And you can't see it immediately like this. And of course, there's not a person looking at it every time. They actually only look at it when the machine fails. When they have to stop it for some reason, or the machine stops, I mean, the band stops because the motor didn't have enough output to keep on moving it, they had to stop it, and they know that there was an error, so they had to go into the time series and locate the windows where it happened, and then they say, okay, it happened at 1720, and they register on the logbook and everything. So it's a very, very non-automated thing, and they don't have the I would say system there in place to detect this anomaly. But they know it occurs. They know how it is. They know how it looks. They can even know when what is the exact signature in these plots of a little bump in the current that means this decrease in the current, and that's what causes the failure. But they don't know when it's going to happen. So we've been working with another physics student, actually, who spent 6 months there in the manufacturing plant, working with the people who are firsthand with this data. And they were exploring, carefully labeling the data and doing some quick models based on different algorithms that are common in machine learning for anomaly detection, which unfortunately I can show you here, because this is sensitive information that we are not allowed by our non-disclosure agreements to show. I mean, I can show you the time series and tell you about it, but I can't show you the others because we have to do this agreement with the companies. So this is another interesting project that we're working on that we hope that strengthens our relation with the company and gives us more stuff to play with. And with that, I want to finish. I want to quickly give some closing remarks. I don't think I have more images here. After this is just more text and talk, but I'll just wrap up on the kind of problems that we think industry is facing, what the industry needs, and what we as the science professionals can actually give us a value proposition for industry. So the different types of problems that industry faces could be grouped in 3 very broad categories. One that can be labeled discipline problems, which have to do with how the worker works. If the driver of the truck allows people to steal fuel from their tanks, well, that's a discipline problem. In other examples that we have worked, which I didn't present here, we know that, for example, in a manufacturing process where they make plastics, we have been told by the managers that they know that their workers steal the final product, and sometimes when they have to do the numbers to see how many product it turned out from a process, they find that there's some percentage of the final product missing, and they know, not because they're watching them, but they know that the workers actually take some to their house. No? So that's a discipline problem. It has to do with a lot of the organizational culture of the country. Like Japan is a good model for that. No, another category of the problems that industry has is in systems. So they have to do more with the processes, the equipment, the assets, and how they work, how they are designed, how able they are to manufacture and endure. For example, in the company that does telemetry and that we work together with their trucks, they have a process in which they try to renew their fleet as soon as they can. But renewing those fleets it's an expensive investment. So they have to make sure that they have the best equipment and they have the best systems and processes. And one example of this countries that do well on this is Germany. Germany has a very strict design and manufacturing control. And then another category could be the intrinsic, which it has to do more with what's your relation with the customers and what's your take on intellectual and collaborative. And of course, this is how you look to the outside and how you are able and willing to and open to collaborations like the ones we are trying to pursue here with the companies. And you can see none of the model countries are Mexico. Mexico has a very particular view, like companies in Mexico have a very particular view of how to go outside and reach for collaborations. So the industry needs, of course, improvement in their quality and their processes. They need to waste or they need to have less waste and be more efficient. For example, with equipment, wastes could be like garbage or the products from transforming the raw material into a final consumer thing. And there's a lot of energy wasted there. So how do they reduce that waste and by hand use less energy? They have a lot of fragmented problems, and most of these problems need quick solutions. One of the things that we have learned and observed is that companies don't care if they already solved a problem. They don't care. They don't care if you come and say, oh, I have a better solution to that because I did some research on this, and they don't care because that's a solved problem, and they have to go to the other problem and solve it. So they have this kind of attention span that is not very large, and they just want to quickly fix a problem and go on. But sometimes, especially in big companies, these fragmented problems, even if they are solved, are not integrated among themselves. For example, in the anomaly detection example I was showing you, if the motor fails in this part, then the whole line of production that is related in that part has to be stopped. And so this fragmentation of the problem, of course, affects other parts of their process. They also need reproducibility. The problem with that is that they don't like to give the information, so it's a little bit hard on working in that. And of course, many times they need the actual data. So what can we offer as scientists, as physicists? Well, I have already told you that I work closely with physics students, and the reason is that the skills that a physics-trained student or a physics-trained professional has to confront these problems are unique. The set of tools, the way that we approach the problems, the way we learn to do research, how we think towards a solution, in general, how we are trained, is a very valuable asset for these companies and for these needs. I mean, we've had experience with many students in different areas, and consistently those in physics, even more than people in engineering who are more oriented into these kind of problems, into these kind of trainings. The people who study physics is just more outstanding in this. And I'm not saying it because I am with a physics audience or I'm a physicist. I'm saying because it's what we have seen. And actually companies have told us, what did this guy study? Because he's really good at looking at this and understanding this. And what they have studied is physics. So it's a very interesting fact that we have consistently seen. And we have tried to take advantage of that in many senses, looking for students in physics that are interested in this, line, to place them with the companies. The companies are very pleased with that, and they are very happy with the fact that we send them physicists, and they are quick in learning and quick in actually working towards solving the problems. And okay, so yes, so these are some of the value propositions we have. Some of the bottlenecks that we have encountered along all this trip is that, with no particular order, but in our country, the relation between industry and academia is I said very narrow, but I actually meant the contrary. It's not narrow, it's very large, and we are seen with mistrust. So as if we want to get into this from the academia part of view, I mean, we're not going to solve the problems, but we have to learn how to approach these companies, and also learn when to say, well, I don't care and I don't mind, and just go and move on. I mean, many companies say, oh yes, we are interested, and they let you go all the way down, but then in the end it's just a waste of time. That happens too. We have kind of learned how to approach them, or which companies to approach in order to try to be more effective with our time. These things take a lot of time, a lot of time. I mean, for example, for the data challenge event that we have, we spend the whole first semester after the event, which usually occurred in October, but we use probably up to May, June, just trying to contact companies and visiting them and speaking to them and presenting our case and telling them this is what we do and we want to do this and we present. And for every 5 companies that we visit, if we're lucky, 2 of them respond. So we have to focus our energies into one of them that's the best, or the one that we think is going to be more interesting for the challenge. So it takes time. It's a different road from academic path. As I said, rapidly, companies don't care if you publish, especially in this type of companies. Maybe if you go to more technologically oriented companies like Google type, Uber type, or those that are selling now like financial technologies companies, and even those, they're not very much interested in doing publications and these kind of things, and they don't have the time also. And in Mexico, not many companies have a research and development department or research and development part which actually does research inside of the company and publishes, like maybe you have seen in companies like Google, Facebook. AT&T was famous for that too, Intel, etc. But companies in Mexico don't have that culture. Also, Mexico we are still behind in the road, in the path to Industry 4.0, despite many efforts that we've been trying to push and convince and move forward to. In Mexico, these changes are very slow, and honestly, with the last governments that we've had, both regionally and at the federal level, it makes it more slow. I mean, there's not real investment for our country to move on into Industry 4.0. There were some efforts previously. There's some states that are being pushed much more because of the international investment happening there. For example, Querétaro, Aguascalientes, Monterrey. There's a lot of companies that come from outside Mexico that are pushing for this, but it's not a Mexican initiative or investment. So it's very difficult. It's hard. And what does that mean in terms of what we try to do is, there are few companies that actually have the data to work with them in these kinds of propositions of value. Nevertheless, we're going to get there. I mean, at one point, just because the competition that's coming, and Mexican companies will have to face this road and actually move forward that. And one of the other values of participating in this is that it's a good moment in Mexico to be part of it as a professional with the capabilities to actually work in these kind of things. Now, the last one I wrote it as a kind of final reflection. I think that if you're interested in looking at this line of work after completing a master's or a PhD, one way to start is to maybe think about how could you orient your current research subject or ideas into these applied areas. I'm sure that you will find that it is possible to to do some mental mapping of how I could use it here. It's not necessarily what you're doing as a research for your PhD or what you're currently working with, but more on the tools that you are creating for yourself, which are more useful to get into this. And I think with that, I finish. I thank you very much for your attention and for your time. And I'm open for questions if there are any.
Thank you very much, Dr. Horacio. Now the question session. Well, I have some question from
No question.
From YouTube. Okay, Daniel Vargas has one question.
Okay, go on. See, the way that we have managed to do it is indeed with that type of interaction. I mean, there are many ways of doing it. The way we have found useful and how would I say it? It's also convenient in many senses. It's convenient for the student. It's convenient for the company. It's convenient for us because I don't have the time to do all this, right? Who better than doing it than a student who is enthusiastic and interested in learning these kind of things. And for companies, it's good for several reasons. Maybe not at the level of a master's or a PhD, but or a recent graduate. But for companies, students are kind of cheap. I mean, it's not too expensive to have a social service student working with you 3 months while doing some work in your plant or in your group or whatever area he's assigned to, being paid by the company. This is most of the serious companies actually get some payments to the students. And in the end, what they do is they see how the student develops, how good he is. They test him, they try him, and in many cases, which has happened, they offer him a job after that. They tell the students, okay, if you want to be hired by the company when you finish your professional studies at the university, come and look, because we already know you. You already been trained with us, and you know the process, etc. And so they have an open option for them when they graduate. And something similar could happen at a PhD. It's just a longer way. It's probably going to take a little bit more, or a completely radical way of changing how to do it. But it's doable if that's the professional line that you want to pursue. So it has worked for us because in some way we can also help students to find some placement when they finish. You see, many students here in our university that are studying physics or sciences, they're not really sure they want to go into the master's or PhD program. And we've seen that change a lot, and we've also seen them looking for other options, and this has opened an option for many of them with success. But I'm sure there are different ways to do it. It's just that this is the one that has worked for us. And
okay, may I ask another question?
Yes.
So what would you recommend to a PhD or master, a grad student that wants to try the industry? Because
what I would recommend
okay, sorry. Yeah, go ahead.
What I recommend, and the way I operate with my students here, most of our students have to do a professional residency at some point of their graduate program, both a master's and and PhD. And of course, if you're pursuing a PhD, you want to do your residency probably on a research group with similar interests to what you're doing, or where you could learn something related. But for the students here who want to go into this direction, I usually recommend them to do their social service or their professional residency in one of these companies. And if they are willing, they agree, then I look for a way to place them. No, so I ask them, well, what is your particular interest? Where would you like to work, or what kind of things would you like to do in the company if you want to go over there? And with that knowledge, I call a couple of the people I know from the contacts of networks that we have with our partners, and I ask them, look, I have this guy, he might be good with you, or who do you recommend me with? Or I call the other. Then if it's a professional residency, they usually take them because it's very cheap in terms of workforce, no? And it's very valuable because these kids go and actually do solve their problems, or help them work them out, no? So I would recommend to take that opportunity of identifying an industry where you would like to have the experience, and use that time of your professional residency, if it's possible, to experiment, because it will also give you, like a hands-on experience that you could say, this is not for me, no? Or you might just say, wow, this is what I was always hoping for, and you stay there. I mean, I've had, I know of students that have been in both sides of the coin, and it has worked fine. Some of them have come back to the academia and they are pursuing a PhD. Some of them just stayed there and are happy as they can be.
Or last, I'm sorry. Okay.
No.
Okay, but let's say that a student didn't had an approach like social service or professional residency in the bachelor's, neither master's degree or PhD. What do you think is a better approach of a physicist for going into the industry? Just like having your mentor to ask his contacts in the industry, maybe? Or what would you say about that?
That's a little bit harder. You're cornering me there. So if you didn't have the chance to go and do a residency, I don't know. I think it's a very personal choice. It would depend a lot on what the particular plans of the students could be. For example, if a student was not interested in going further in academia anymore because for some reason, whatever reasons, he's not, he doesn't want to continue there, then it might be a good chance to just, leave academia for a while, and instead of looking for a postdoc, go and find a company to work for in the next year. And it'll take you away from the academic path, yes, and it'll give you this change, but it's still not impossible to get back to academia. It'll be harder, yes, but it's not impossible to get back. And you will have had or the student would have had a chance to get to know from closer, have that experience. And of course, there are many industries, and another opportunity which here it's a little bit more difficult, but there's also companies in the United States, there's companies in Canada, and there are companies in Europe that are looking for this kind of professional capacities of the students. The only problem there is the United States, Canada, Europe certainly is more competitive, or there's more competition there than here. So you're going to be having probably more options in there, but it's going to be harder too. And here in Mexican companies, there's going to, I think more and more options are going to start appearing. And if it's an interest that a student has, I guess it's a risk that it's worth taking for using their skills and going into a kind of postdoctoral research position, which is not a postdoctoral nor a research, but is working for a company. But another, just by talking, another thing that comes to my head, which I would recommend to any student looking at this, is also don't look at the companies that are, like we always tend to turn our head to the big companies. Oh, everybody in Veracruz here wants to go with Tenaris because Tenaris is a big company and it has a lot of resources and it has a lot of fame and everybody knows Tenaris. So everybody wants to work there because it's a huge company. So in my experience, the smaller companies, medium-sized companies, those that are not these huge multinational monsters, are more interesting and more productive, and they have more problems and more need to attention to their problems. And also these smaller or relatively newer companies are probably more oriented into the new idea of using data and becoming a digital company in the sense of actually using data for getting into the process. So don't look at the huge big companies. Those are very hard monsters to move and to get in. They move very slow. They have their own particular problems and they do the things like they do them and they don't care if it already works, keep on moving. Instead, look at medium-sized new companies, probably not these, not so new that they just starting, not these startups that are just opened last month, but companies that have been in the road for about 5 to 10 years and that have a profile of or interest of using data. That's it.
Okay. We have a question or many questions from Soham. So Soham, please.
No, I just have one question. Horacio, if you get some industrial data to work on some of the problem, some of the problem where they want some solutions, could you use those data to form a problem what you can work on and then publish? For example, this network thing. So maybe they have some specific problem for which they want a solution. But can you study this network from an academic point of view, for which is created by their data, and later on publish?
Yes, Soham, thanks for the question. That's a very good question. And in this particular example that I'm showing you, yes, we are allowed to work with use the data to publish, as long as we don't mention any names nor reveal, so to say, any particular details of what the companies are. So we can't say, I said Coca-Cola, but I'm just using a generic example. So there are some basic disclosures there that we can pass, or that we can that make no problem to publish this. So yes, that particular data is publishable. When we do this, we have to show them the work before submitting for publishing. And in the 2 cases that we had the chance to do it, but then the student didn't finish it, they agreed to publish it, as long as we didn't put like a specific particulars of what was mostly because they're protecting their clients, not because they don't want to make this information public or available. They're protecting their clients, but in that particular partnership, we are allowed to publish. But it takes time. It takes some time to do it. In others, we're not. For example, in the anomaly detection example that I show you, we don't have a complete authorization to publish yet. We're looking for it. I mean, it's a process that we have to go through by many ways, which makes it tedious and makes it long and takes a while. But one of the things that the data challenge has helped It's actually to create this trust between the companies and us that allowed us to, when we reach the point where we want to publish using the results, they are willing to do it, no? As long as we do it in a correct way. And we try to take care of that because otherwise we don't want to lose the contact, the partnership, and the collaboration that we have. But fortunately, up till now, we have worked with companies that are open to that, as long as we are careful and follow their guidelines. And bigger companies have more strict and complicated guidelines. Medium, smaller companies are a little bit more flexible.
Okay, thank you. That's all.
Thank you, Soham. Ken, please.
Yeah. So my question is, I heard I heard the response you gave to Daniel a bit minutes ago. You said that you were, I mean, it was a bit more of interest in smaller companies than in bigger companies. However, I wanted to ask you if you are interested in big companies. For example, I work at Oracle. Oracle is a database and also is becoming one of the largest cloud-based computing. And also, I worked in HP, and there are very, as you mentioned, they are also interested in contacting, like recruiting talent, right? Getting to know each other. So in that sense, are you interested? Even, I mean, there are other companies such as Continental also. I could maybe the automotive industry. I could also make some contact, but I'm not sure. First of all, I'm not sure if they're willing to, because I'm not sure if this organization is that renowned. And the other thing is that I'm not sure if they're willing to like collaborate that far. I mean, I know HP has tried a collaboration with CIMAT, which is this mathematical institution. So I guess there will be also willing to, if they're like very a fun like a renowned organization, then they might also be interested. So my question to you is, are you also interested in big companies or rather smaller companies, medium-sized companies?
Thank you for your question. If I said that I'm not interested in big companies, I said wrong. I didn't use the correct words.
No,
not that we're not interested in.
But you're
of course, we are interested in big companies.
Okay.
For example, Tenaris, which is a big company here, it was on the top of our list at the beginning of this, no? And we got pretty far with them until we got like wiped out from their attention, and they didn't for a while were not interested in these things until for some reason we got again a contact with them, and we showed them, invited them to the data challenge, and they were really very interested and willing to participate on it. So it's just, you know, the life turns around, and then you find the same guy later, and stuff happens, and it's okay. We are interested in big companies, of course. It's just that big companies take more time, and you have to have the right contact, and you have to, you know, be maybe in the right place at the right time with the right person, and that's hard with big companies. So it's not that we're not interested, it's just that it's more difficult, and we have found that with smaller, medium-sized companies, which you can more quickly be in contact with the whoever is responsible for actually taking a decision. The problem we've had with big companies is that in order for the guy who can give us the data to give us the data, once he said, oh yes, this is a very interesting thing, well, he has to go to his superior. He has to convince his superior that it's worth, that they should give the data to me and to our organization because we have proven worthy. And supposing that he convinced that first head has to go to the next hierarchy level and so on until they get to the top advisory board of the company. And they have told us in the big companies, you know, it's really, really hard to get these kind of things into the advisory board. The case with the Nari Stamsa happened to be one case in which the person that was the contact there, or that is the contact there, is a very high level person on both sides, on the administrative hierarchy and on the actually manufacturing hierarchy. So he's somebody with a lot of influence, so he can actually make both sides say yes and not without problems. But in other companies, it's just in one of those steps on the ladder of hierarchies, it gets lost, and it's a lot of work that is invested. We have a very good approach with another big company, which is Danone. You all know Danone, this French company, and it has taken us years to be able to get into something, just because of this big levels of hierarchy they have. And we found that with smaller companies, the steps are lower. Many times, the same guy who you're talking at in front of the computer is the guy who takes the decisions on the floor, and he can actually change things and or actually say, yes, we're going to do it because I am the boss and I'm the chief officer and I can make it happen. So that's the reason why we look mostly into smaller, medium companies, no?
Yeah. Okay.
But if you have contacts and you know people, it's always good to have those contacts and give them a call and just try to establish it.
Actually my boss is giving out some of the data to some universities, and he's from the United States, so he's basically working also with Stanford and some universities here in Mexico. But yeah, I mean, he's also making like a challenge similar to what you guys are doing, and I guess I mean, I'm glad that at least the Universidad Veracruzana is working on it. It's a pity UDG is not in it in that sense, but yeah, it would be. I mean, if it's of any help, maybe I can contact them and see if they can make things work out.
Well, that would be very, very helpful, and I would very much appreciate if you could put us in contact through your.
Sure.
Thanks a lot.
Mm-hmm.
Okay, a few questions from YouTube. Betsabe Vasquez is asking, were you grad student working from the master in the SIA?
Again, where is my grad student working?
Yeah, the student from the master in the Centro de Investigación. Where are they working right now, I think?
Well, the two graduate students from the master's programs that have been doing this in these past years. One is from Lania, from the other center that I worked in the past, and he's working at this company of telemetry data, which is it's located in Veracruz. The company is called Telemotum, and so he's now the chief data scientist there in that company. but he was a graduate from the other institution. And from the UV, he's not actually a graduate from the IA program from the Inteligencia Artificial. He's actually a physicist graduate from the master's degree in physics. And he's also looking, he just finished last year amid the pandemic, and he wanted to go and work to Motum also, but I think that he didn't play his cards well, and now he's waiting for Motum to call him and looking for another job now. But we have students that at the master's level too, working in similar things. Some of them did go to a little different line of work. I have students that are working at the Banco Azteca in Mexico City. I have another student who's working in a company that's called the Data Raken Group, which I just knew it existed because he's there. But all of these are not from the IA program, actually. They are from either the other program at Lania, which it's called Masters in Applied Computer, Maestría en Computación Aplicada, or the Physics Masters, no? In IA, my students from IA still haven't graduated yet.
Okay, thank you. And another two questions from Fernando Flores, and also from YouTube, is what companies were interested the most in the opening of the satellite center in Mexico? And the other question is about the relation between the industry and the academia. How is the horizon from these projects and collaboration changing in Mexico?
Okay, the first question about the satellite center that didn't happen at the end. We did not get the renewal from the CONACYT grant, so we couldn't make it happen. We had this company of telemetry on board. We had the truck company that has some of the that has a big fleet, and I don't remember. There was another company. I don't recall which. I think it was a company from Puebla, because this was a joint program with the University de las Américas Puebla, and I don't remember if it was either Clariant, which is a chemistry company, or I don't remember the third company, but I think it was a company in Puebla. And for the second question, if you can repeat me the second question, please.
Yeah, it's about the relation between industry and academy. How is the horizon from these projects and collaboration changing in Mexico?
Well, it's a very far horizon yet. I think it's slowly changing in many senses from the academia point of view, driven by the fact that many of our graduate students graduated students from our different programs. I mean, I move in the physics and the IA programs because that's where I am employed, but it probably also on other different areas of study happens something similar. But our students are looking for different options after they graduate. Of course, as a researcher, we want to, or I still want also to be able to get the best graduate students and have them work on a project with us. But it's a fact that many of the students that are doing their masters in these programs, they don't want to do a PhD, either because it's not clear what's the path, to get a position as a PhD graduate, or they just are not interested in doing it and they don't want to continue with graduate studies above masters. So they are looking for different outcomes, and many of them, because they're young and they're growing in this new digital era, and they're part of it. They produce part of this digital data. They know that there are other options over there. They're interested in them, and they're looking for them once they graduate. So they ask. No, they say, hey, where can I go? I want to do this. I don't want to do physics anymore, and I want to do. And it's our job at some point to help them get placed and find the best location for them to continue developing professionally. So it's not like I can force them to be my master's students. Or there's the other type of student who is sure he wants to go to a PhD and that's it. So I think it's a slow change that it's driven by that graduated students are looking for this option or options, and this is one of the options that it's available or they look for. And also slowly, and as I mentioned, companies are changing also, and they will have to change. They will have to adapt. Maybe it's not happening as fast as in other countries because we don't have a thorough government plan. I mean, many of these changes in industry around the world happened because it was also driven by the government. Germany, United States, Japan, they all have government plans for actually going into this next generation of industry. And we are not, but eventually we will have to. So I think that the companies that will actually survive, and I'm not talking about the huge big companies like seminaries or Cemex, no, I'm talking about smaller companies that today are in the market and are competing and are doing well. They have, or their competitors will have to evolve into a more data-driven way of doing their processes. So it's eventually going to happen, and they're going to be looking for people who's capable of participating and doing things there. So it's an horizon that it's slowly showing, very slowly, but it's there. It's there. I mean, it's inevitable, no? It's not like we can just close our eyes and say, no, it's not going to happen, because it's happening around us and it's happening in some of the companies, and they need it. I mean, and it's in many levels. I mean, many levels of companies and sectors. There are right now a lot of companies of these startups that are looking for generating some kind of opportunity value from problems that you could identify, or that you could say, oh, there's a good portion of critical mass that it's willing to pay for a chip for my dog. Also, let's do a company that has everything so that we can get the data from the dog, and et cetera, et cetera. And then they run a startup, right? Those are different problems from a new sector of industry that is also emerging. But what we're looking more is at the companies that are actually producing or participating in a more bigger sense of the economic process. Right? For example, companies that actually are moving and creating some value by transportations or manufacturing, et cetera, et cetera. So it's an horizon that's there. It's going to come to us, and we're going to have to go towards there. And how have our experience worked? I think in our small regional experience, we've had a good opportunity to actually contribute to the different agents, so to speak, that are participating on this. And on one side, the companies, I mean, they are being benefited by the fact that we can find and we can train good professionals that are capable of doing this kind of work. and they are consuming this kind of work, and we are learning the problems they have, and we're having access to their data to keep training these students and to do some research and ask different questions. For example, this particular example of the networks from the city, like the student set it up here, is not a question that the company has. It's a question that came from our interests and the opportunity of having that data. And on the other side, to the students that graduate and are looking for a different opportunity or a different outcome. So I think this particular effort that we have been doing in that sense has been very successful in all the sites that are participating. Thanks.
Thanks a lot, Dr. Horacio. I don't know if there are more questions. I think no. Okay. Well, thank you very much, Dr. Horacio. Thank you.